So starting today, we'll be discussing binary trees, right? Let's take a binary tree. Can you see this?
Yes.
All right. So binary tree has a root and there is a concept of child nodes. In a binary tree, there are two children of every node. Every node has two children. The node of a binary tree has one data and two pointers, right? One pointing
Yeah.
to the left child and one pointing to the right child. Can I say that this binary tree is a binary search tree?
Yes.
All right.
You can. Yes.
Right. So this is a binary search tree, but we are discussing binary trees only right now, right? So we
hmm
will not use the binary search property of this tree, right?
Okay.
All right. So all the data structures that we have seen till now are linear in nature.
hmm
For example, linked list is linear, stack is linear, queue is linear, array is linear. All of those data structures were linear. If it is a linear data structure, then you can traverse it in only two ways. Either you start from the first element and move forward, or you
Right.
start from the last element and move backward, right? Essentially, there
Mhm.
are two ways of traversing a linear data structure. These are the two ways, right? But
Right.
if it is a hierarchical data structure like a binary tree, then there are so many ways in which you can traverse this, right?
hmm In
So,
order,
for example,
pre-order, post-order.
sorry,
In order, pre-order, post-order, right?
yeah, but I mean, in order, pre-order, post-order, there are three ways, but there can be more ways. For example, let's say this is level 0, right? This is level
Right.
1, this is level 2, and this is level 3, right? One way of traversing the tree is that you go to each and every level in increasing order, and for each level we will be traversing the tree from left to right. Therefore the
Okay.
output will be 5, 3, 15, 1, 4, 6, 20, and 9. Another way can be
Okay.
that you consider the levels in increasing order, but now we are printing every level from right to left. In this case, the output will
Mm,
be 5, 15, 3, 20, 6, 4, 1, 9. Another way can be that we are still considering the levels in increasing order, but now we are printing every level alternately. So the first level is printed from left to right, then from right to left, then from left to right, then from right to left, like that,
okay.
right?
Yeah, I see.
Uh, Another way can be that we are considering the nodes in reverse order of level order traversal,
hmm
right? Then this is just horizontal levels. We can also consider vertical levels. So what I'm trying to say is that there are so many ways in which we can traverse, in which we can visit each and every element of the tree, and most of the questions are on these ways, right? So some questions
Right.
require you to traverse the tree in pre-order, some in post-order, some in mix of pre-order and post-order, some in level order. Sometimes you are traversing the right subtree first, then the left subtree, like that.
Yeah.
All right.
Okay.
All right. Now let's come to the major three traversals that you were talking about, which is pre-order, in-order, and post-order. And we'll also come to the level order later. All right. So what is the pre-order traversal for this?
Okay. Pre-order is root left right. So it'll be 5, 3,
Mhm.
5, 3, 1, 4, 15, 6, 9, 20.
Great. What is the in-order traversal?
In order is left root right. So it's going to be 1, 3, 4, 5. Right. Would it be 15 or would it be no, it'd be 6, right?
Mhm.
6, 9, 15,
And 20,
20.
right?
Yeah.
Right. What is the post-order?
And then post order will be left right root. So it's going to be 1, 4, 3, 9, 6, 20, 15, 5.
All right. Great. Right.
Right.
So, some basic things. One is that 1, 4, 9, and 20. These are the leaf nodes, right?
Yes.
Okay. If you look at the pre-order traversal, the order in which the leaf nodes are getting printed is 1, 4, 9, and 20. In the in-order
Mm-hmm.
traversal also, the leaf nodes gets printed in 1, 4, 9, and 20. In the post
Right.
order also 1, 4, 9, and 20. Right?
Okay.
So in all of these three traversals, the order of the leaf node is the same. The relative order of the leaf nodes is the same. All right?
Yeah.
All right. Second is that the in-order traversal is sorted. Right?
Yes.
Okay. So if you have a binary search tree, then the in-order traversal will be sorted. Right?
Yes.
In fact, sortedness is both the necessary and the sufficient condition for a binary search tree. I mean,
Yeah.
if the in-order traversal is sorted, then the tree is a binary search tree, and if the tree is a binary search tree, then the in-order traversal has to be sorted.
Okay.
All right. Next, let's say you are not given the tree, you are only given the pre-order and in-order traversal. Right. So you are not given the
Mm-hmm.
binary tree, you are only given the pre-order and in-order traversal. Can we build the tree from these two traversals?
So the first one is going to be the 5, 3, 1. So you know that that's as far as it goes, and then that's as far as the left one goes, because on the
So
left one, right?
from the pre-order traversal, we can only conclude that 5 is the root.
Yes.
Right? We can't say that 3 is on the left, right?
Mm-hmm.
Okay.
From
So
the
from the
left
pre-order
in
traversal,
order.
from the pre-order traversal, we have concluded that 5 is the root. Now we
Mm-hmm.
look at the in-order traversal, and all the nodes on the left side of 5 belong to the left subtree, and all the nodes
Right.
on the right side of 5 belong to the right subtree.
Yes.
Right? It means that on the left of 5, we will have 1, 3, and 4. And on the
Mm-hmm.
right of 5, we have 6, 9, 15, and 20. Right?
And then you just repeat that for 3.
Yeah. So out of these 1, 3, and 4, we will see which one comes first in the pre-order traversal. 3 comes
Right.
first in the pre-order traversal. It means that 3 must be the root of this tree. And then
Yes.
we again look into the in-order traversal, and because 1 is coming on the left and 4 is coming after 3, it means that 1 must be on the left and 4 must be on the right.
Right.
The same goes for the right side. Out of these, the first node is 15. Therefore, 15 is the root of this tree. And
Mm-hmm.
6 and 9 belong to the left side, and 20 belong to the right side. Right?
Right.
And then we
And now
can
6
figure out
comes
that
first.
6 is the root. Yeah,
How do you
6
know
is the
15
root.
is the root? How do you know 15 is the root?
Because, okay, look, 1 and 4 are already here, right?
Okay.
So 15 is the next number in the pre-order traversal. That's why, it's the roots.
Yeah. So out of these 4 nodes, which one comes first in the pre-order traversal? In the pre-order traversal,
That's how.
15 comes first, right?
It's root, then left, then right.
Okay.
So 15 comes
No,
first, right?
but what the chit told is also right? Like if we know that 5314 is covered, the next one is 15, right?
Well, that's what he's saying.
No, but then
Yeah,
he's
yeah,
saying
it's the same thing. It's the same thing. So basically, we have to exclude all of these nodes, and we have to consider only from these nodes. This is fine, right?
no. My question is, how do you know
Uh-huh.
15 is the root?
See, let's start from the beginning. From the pre-order traversal, can we say that 5 is the root?
Yeah, because it is starting, right? So we know that
Because
5
it
is
is
the
the
root.
starting. So we
Yeah.
we figured out that 5 is the root. Now now forget the pre-order traversal. Look into the in-order traversal. In the
Yeah.
in-order traversal, search for 5. 5 is there,
Yes.
right?
Yeah.
Now the
This part
in-order
I got.
traversal is
Yeah.
now from the in-order traversal we can say that 1, 3, 4 belong to the left side, and 6, 9, 15, 20 belong to the right side, right? Now
Yes.
consider only the right side. In the right
Okay.
subtree, there are only 4 nodes, 6, 9, 15, and 20, right?
Yes.
Out of these 4 nodes, which one comes first in the pre-order traversal will be the root of the right subtree,
Yes. Okay.
right?
That's all.
So we see that out of these 4, 15 comes first. Therefore, 15 is the root.
Yeah.
All right?
So we check which comes first, right? Not the
Yeah.
chit. What the chit told is we see
See,
if 5314
it's the
is
same thing, because because
Yeah.
134 has already gone on the left side. It
Yeah.
means that all of these nodes are already considered. Now what
Yeah.
comes
But
first?
what is the optimized way to do it? Is it just the next one is the root? Because all of that is covered, that's why next is the root, or there will be scenario where we will not have that kind of use case like where 15 is not next.
But
See, it
it's the
depends
property of
on
the
whether you are,
traversal.
Yeah.
in case you are building the right subtree first, then 314 will not be already considered. But
Yeah.
because we are building the left subtree first, so 314 is already considered,
Okay.
right? I mean, it depends on how we are building the tree. If you are building the right subtree first, then you don't have any information about 314. Then you have to look
Yeah.
for the first node out of these four. But if you have already built the left subtree, then whatever is left will be only the right subtree, because root is already
Okay.
gone, the left subtree is already gone. So
So
whatever is
then
left in the pre-order traversal is the right subtree,
so
right?
then that is the optimized part, right? Like if you build the left, then you immediately go to the next and you know that this is the root, right? Rather than looking out of the four, right, Kamal?
Yeah. So it's basically the algorithm that we are looking at, right?
Okay. Okay,
Okay.
got it. No,
See,
I was just confused with that part.
no, that's okay. That's okay. See, how do you define the binary tree? I mean, academically, the definition of binary tree is that binary tree has a root which is either null, right? Or it has a node which has a data and two pointers pointing to the left subtree and right subtree, and both of them are binary trees, right?
Yeah.
So the definition of binary tree is in terms of binary trees, right? It's a
So
natural
it's just a
recursion.
definition.
It's a natural recursion, right? Which
Yeah.
means that either the left subtree is null or the left subtree also has a node which is the root of the left subtree. Either the right
Hmm.
subtree is null or the right subtree also has a node which is the root of the right subtree, right? So what I
Yeah.
was coming to was that most of the binary tree problems are solved like this. In the binary tree
Okay.
problems, we consider three things: the root, the left subtree, and the right subtree. Out of these
Yes.
three, root is a single node, and left subtree is an entire binary tree, and right subtree is an entire binary tree. Okay.
Yes.
Now, because we are implementing it recursively, the problem at root will be solved by my own function. So I will only focus on the root, and the
Okay.
left subtree and right subtree will be delegated to recursion. Okay.
Got it.
Okay.
Got it.
In the pre-order traversal, how did we define the pre-order traversal? That first you print the root, then you print the entire left subtree in pre-order, and then you print the entire right subtree in pre-order, right?
Hmm.
All right. It's a natural recursion, right? So we are defining it recursively. The pre-order traversal itself is recursion.
Okay. Got it.
All right. All right. One of the reason why we are discussing this is, let's say you are given a binary tree and you want to serialize the binary tree. You know what is serialization, Rachit?
No.
No. Is it like converting it to just like line or like
Yeah. So
Line one.
basically, let's say this tree is given to you. Now this tree
Hmm.
is built inside the RAM, right?
yes.
Okay. If your system shut down, let's say you close the program. If you shut down the system, or if you stop the program, then this entire tree will be gone, right?
Yeah, so how do you save it basically?
How do we save this, right? So one of the use cases of serialization is that, if I know how to save it, I can pass it to the network also. I can pass it over the internet also, because over
Right.
the internet I cannot pass the address of a node, because address of a node is local to my machine,
Yeah.
right?
Hmm.
So serialization has two use cases. One use case is that if you are able to convert this into a string, then I can pass it over the network. And if you are able to
Yes.
convert it into a string, then I can store this in a file, right?
Right.
Hmm.
So when I was interviewed for Microsoft way back in 2013, at the director level, the question which was asked to me was that you are given a binary tree. I want you to write two functions. This is the binary tree. I want you to write two functions. First function should write this binary tree into a file, and the second function should read this file and build the exact binary tree, right?
Ah.
So essentially,
Okay.
the question was that how will I serialize and deserialize the binary tree?
Hmm.
We will look at this problem in more detail later, but for now, you can also have one solution as In the first line of the file, you will write the pre-order traversal. In the second line of the file, you will write the in-order traversal, and then you can build the tree out of that.
Yeah, we had a
Okay.
problem like this in computer science.
All right, great. Right. This is fine, right?
Yeah.
Okay. Can I say that if I am given only the in-order traversal and the post-order traversal, then also I should be able to build the tree?
Yes.
It's the same thing. From the post-order traversal, the last node in the post-order traversal will be the root,
Yes.
right? And I can use the in-order traversal to divide rest of the nodes between the left subtree and the right subtree. All right?
Right.
All right. If I am given only the pre-order traversal and the post-order traversal, can I create the tree? I'm not given the in-order traversal.
I think you might be able to.
So from the pre-order traversal, we will be able to figure out that 5 is the root, right?
Yeah.
From the post-order traversal also, we can only figure out that 5 is the root.
Right. And the
But we
number
will not be,
before the number
but we will not
before
be, but we will not
is
be
the
able to
right.
divide. Let's say the pre-order traversal is 5, 3, and the post-order traversal is 3, 5. So we know that 5 is the root. But if 3 is here, then also the pre-order traversal will be this and post-order traversal will be this. And if you have a tree like this,
Yeah.
then also the pre-order traversal will be this and post-order traversal will be this, right?
So it won't work.
So for both of these trees, we will have the same pre-order and post-order traversal. So we will not be able to build the tree if we are given only the pre-order and the post-order traversal. All right?
You need the in-order traversal.
We need the
In order,
in-order traversal.
you need in
Okay.
order, but if you given pre and post, you cannot build the binary tree.
Yeah.
Okay. This is fine, right?
Yeah. Your
All
question?
right.
No.
Now let's say we are given this binary tree. Let's take the same binary tree. Let's say we want to write the pre-order traversal. So you know already the pre-order traversal, right?
Right.
Okay. So let's quickly write it. The pre-order traversal will be, so we'll say that if root is null, then don't do anything and just return. Otherwise, system.out.println root.data, and then pre-order root.left, and then pre-order root.right. All right.
Right.
How much time will it take?
O of n. It has to hit
O of
every
n.
node.
O of n, right?
Yeah.
Great. So this is fine, right? Till this point, it is academic. How much memory will it take?
O of n as well, because you have a call for every node.
O of n. Okay. Can I say that the exact memory taken will be equal to the height of the tree?
Yeah.
Yeah, true.
True. So can I say that if the tree is balanced, then the memory taken will be O of
O of
log n,
log n. Yeah. If the
right?
tree is balanced, yeah, O
Yeah.
of log n.
I mean, in the extreme case, you may have the entire tree on the left side. In that case, the height of the tree will be equal to number of nodes of the tree. So in that case, your answer will be correct because it will be O of n.
Wait, so why is the
So,
memory O of log n?
so let's see. First, when you call this function, the function will be called for 5.
Yeah.
So it will print 5 and then call the function for 3.
Yes. Oh,
Then
it
it will
pops off as it goes, and then when it
exactly,
goes to the right. Yeah, I
exactly,
see.
right? So then it will print 3 and call the function for 1. Then it will print 1 and call the function for the left side of 1, which is null. Then it will return and call the function for null again, right? So it will call the function for the left of 1 and then the right of 1. Then this will return and this will return. All right.
Mm-hmm.
All right. Then 1 will also return and the function will be called for 4. Now the stack frame of 4 will be created at the same place where the stack frame of 1 was there.
Yeah. Oh, okay, I see. I see.
All right. And
Yeah.
if I'm not, so let's not print nulls. So then 4 will return, then 3 will return. Then the stack frame of 15 will be created at the same place where 3 was there. Stack frame of
Yes.
6 will be created at the same place where 1 and 4 was there. Stack frame of 9 will be here. Then 9 will return and stack frame of 20 will be created here, right? So all the nodes which are at the same level, the memory will be allocated to those nodes at the same place. So, there is no
Okay.
extra
Yeah.
memory in that sense.
Yeah, that makes sense.
All right. Can I say that this tree can I say that exact, the number of stack frames exactly is equal to height of the tree plus 1,
Yeah.
right? Because, ultimately you will be calling it for null also. All
Yes.
right. All right. Great. How can we improve, or can we improve this function further?
Mm, you can check if both child nodes are null, then you just
Okay.
don't do the pre-order.
All right. So let's see. Uh, so if I put a check, if root dot left is not equal to null, only then call it, right?
Yeah.
Similarly, if root dot right is not equal to null, only then call it. All right. My
Yes.
question to you is that, so I was also hoping this. My question to you is it an improvement or is it the same? Because we are reducing some function calls, but every function call is getting more expensive now. Because in
Hmm.
every function call, we are performing 2 extra checks.
I guess it only works for the leaf nodes.
Yeah,
So it's not
I
worth.
mean, it will only reduce the number of calls for leaf nodes. Now we won't be calling the function for leaf nodes, right?
Yeah. So
So is it an improvement or is it not an improvement?
not an improvement.
So let us see how many leaf nodes are there. Instead of leaf nodes, let's say how many pointers are there. So the number of node, if there are n nodes in the binary tree, then there will be n plus 1 null pointers in the tree.
Right.
All right. So here you have 1, 2, 3, 4, 5, 6, 7, 8. Here we have 8 nodes and there will be 9 null pointers. Left and right of 1, left and right of 4, right, left of 6, left and right of 9, left and right of 20. Right?
Yeah.
So how many times are we calling the pre-order traversal? Pre-order traversal will be called 8 times for valid nodes, right?
Yeah. And it's stopping 9.
And it will be calling 9 times for null.
So it is an improvement.
It is an improvement, right? All right. So what happens is that if you put these checks, then the number of function calls will be reduced to by half, right?
Yes.
So inside every function call, we are having these 2 condition checks, but the number of function calls are reduced by half. And function call is a very expensive operation because function call is linked with function return also. So that's why this is
Yeah.
this is an improvement. So going forward in the functions of the tree, I will not be putting this check. This check is understood. Most of the interviewers also don't go this deep. But sometimes, if the interviewer gets into the discussion, then these kind of things will create a wow factor in the interview, right? Because
Mhm.
most of the interviewers have not thought about these things. Most of them, almost all the problems of the binary trees are solved either using recursion or using level order traversal.
Level order traversal?
Yeah, we'll come to that. So it's like 80 to 90% problems are solved using recursion and
Yeah.
10 to 20% problems are solved using level order traversal. Because a binary tree is a special type of graph. So when we discuss graph later in the course, for graph also you will find that we have largely 2 strategies, recursion and level order traversal. So when we discuss graph, we will call recursion DFS, depth first search, and we will call level order traversal as BFS, breadth first search. Pre-order, in-order, post-order. All of these are basically recursion. All right. So today and probably tomorrow also, we will focus only on recursion. And then once we are done with the recursion, then we will go to the level order traversal. All right. So while solving the binary tree problems recursively, our focus should be on solving it for the root and leaving the left subtree and right subtree to recursion. So this should be the strategy. Okay. Now, let's take an example. Let's say we want to count the total number of nodes in the tree. Integer count nodes, node pointer root.
Right.
Yeah,
So
go ahead.
if
Mm-hmm.
root equals null or returns 0,
Uh-huh. Okay. You go ahead.
um, otherwise return 1 plus count nodes root left and then count nodes right.
Great, great. Right. So basically, what we are saying is, to solve this problem for root, we call the function for the left subtree. We
Yeah.
say that, first you count the number of nodes in the left subtree. Let's say this count comes out to be X. Then you count the nodes in the right subtree. Let's say this comes out to be Y. My
And
answer
you
will
add.
be X plus Y plus 1,
Yeah.
right? The problem of counting the nodes in the left subtree is delegated to recursion. And similarly, the problem of counting the nodes in the right subtree is also delegated to recursion. Return
Yeah.
count nodes in the left subtree plus count nodes in the right subtree plus 1. All right, great. Now let's say we are given the same tree and we want to search in this tree.
Okay. Is it a
So
BST or a binary tree?
let's say it's a binary tree.
If r.data equals val,
Okay.
then return true.
Okay.
Otherwise, return search root dot left, same val, and then or search root dot right and then val.
All right, great. So what you are saying is if root dot data is equal to value, then return true and don't search further, right?
Yeah, don't search further.
And you should add the first line also. If r is equal to null, return false. Right?
Oh yeah, if r equals null, return false.
Right. So Boolean search root comma root dot left comma value. So I just want to write it like this, and I want to understand whether this is the same or not. So this will be y and return x or y.
If r equals
So this
null.
is another thing, that if it is a Boolean function, now this is the Boolean function, right? Right. So if it is a Boolean function, then there must be at least two terminating conditions or two base conditions of recursion.
Yeah.
One must
Two base.
be, because otherwise, we are always returning true, right?
Yeah.
So from some endpoint, we should be returning false also.
Yes.
So if root is equal to null, then don't do anything and return false. All right.
Yeah.
Is this code same as what you are saying?
Yes.
Okay. So you were saying this, return search this or search this, right?
Yeah.
All right. So one is this code and second is this code. Okay. Are these two similar, or you want to give it a second thought? 1 and 2.
Well, I know one works because I've done it before.
No, even 2 will work. But are they similar?
Yeah, both will work. Both will work.
Yeah. So what is the difference between the two? Or there is no difference?
There's no difference, right?
See, let's say you are searching for 1. Okay. So if you are searching for 1, then the left subtree will return true.
Right.
Okay. Then you will still be searching the right subtree in the second case.
No, but Java short circuits.
No, in this case, in the second case, you will still be searching.
Oh, yes, yes.
Right. So in the first case, if you are able to find the value in the left subtree, then you will not search the right subtree.
Right.
But in the second case, even if you find the value in the left subtree, still you will be searching the right subtree.
Yes.
What you said was better than what I have written. You understand what I'm saying, right?
Yeah.
Now let's say we are given a value and we want to find the level of that value in the tree. Right? So integer value. And let's say the code is get level. The function is get level.
We have to make a public private pair for this one.
Public private pair
as in do you have your public method and then you initialize a private recursive method?
Okay, so basically this will be your wrapper function. Okay. So what will be the signature of the private function? You will be passing
it'll be get level node r int val and then int depth.
Okay. So int current level, right?
Yeah.
Or the depth. All right.
Right,
Cool.
and you initialize that with 0.
Okay. So the initial value of current level will be 0. So basically the current level will indicate the level of R in the tree. Right?
Yes.
Okay. right? See, even in this case, when you are searching, this function will not search in the entire tree. This function will search only in the tree whose root is R,
Yeah.
right? So whenever we are thinking recursively, we have to visualize the function as if the function is not for the entire tree. The function will be only for some value of R, right? That's why sometimes R will be negative, R will be null also. So I believe that you should be able to write it, right? I think you have already
Yeah.
written this. So maybe what you can do is that give this a try. Let's say we don't want to change the signature and we don't want to write the public private method. Give this a
Mm.
try, right? We want to keep the signature as it is, and we want only this function, no two functions.
You can use a static variable, right? And then that will continue to be same. You don't change,
So
and then you
generally, static variables and global variables, they are not advised, because static variables may have a value which is prior to the calling of the function, right? So it may contain a pre-value. You understand what I'm saying? Static variable, because this function, let's say we are calling this function second time. So we have already called this function first time, and now we are calling the function second time. Though, so that static variable must be reinitialized to 0, right?
You can basically do the Boolean search, but then your return value is just 1 plus if it's there or not. Like,
Okay.
so if you find the value, you go
Mhm.
when you return, like let's say like you return that you found the value, then you just add 1 every single return statement as you go up. Every single stack frame you pop off, you just add 1 when you find the value.
All right, cool. And if we don't find the value, then we can just return -1.
Yeah.
All right. So what this function will do is that this function returns -1 if it does not find the value inside the tree whose root is R, right?
Mm-hmm.
And this function returns, let's say X, where X is the level of value in the tree whose root is R, right?
Yes.
So if value is 6 and let's say root is 15, then the answer should be 1, because the tree
Yeah.
whose root is 15, 6 is present at level 1, right?
Right.
Similarly, if the value is 6 and root is 3, then answer should be -1, because 6 is not present in the tree whose root is 3,
Yes.
right? Similarly, if root is 6 and value is sorry, if root is also 6 and value is also 6, then answer should be 0,
Right.
right? All right, great. So this will work.
Yes.
All right, so let's write the code. So first is that if root is null. If root is null, it means that the value is not present in this tree.
So
So
return
our answer
minus.
should be -1, right?
Mm-hmm. If root.data
Second,
equals value.
if root.data is equal to value, in that case, we have found the data at level 0. So the answer should be 0. Otherwise, let's say x is equal to get level root dot left comma value. All right.
Mm-hmm.
What should be next?
If x equals -1, then you go into root.right.
Okay. So if x is not equal to -1.
Yeah.
If x is not equal to -1, it means that we have found the value in the left subtree.
Yes.
Then we can just return x plus 1, right? Otherwise, what we should do is that we should search the right subtree
Right subtree.
and then return.
Return if x is not equal to if x is not equal to -1, do the same thing there. And then finally at the end you just return -1.
Yeah. So if this is the case, then return x plus 1. Otherwise, return x itself or -1 itself, right?
Yeah.
So how much time will it take?
Is a tree, yeah, it's not a balanced tree, so then it'll take O of n time because you have wait. O
So
of
time is not dependent on whether the tree is balanced or not. It's the
yeah,
memory that is dependent, right?
yeah,
Right.
memory is dependent. So
So
it'll be O of n.
this will take O of n time, right?
Right.
All right. Can I say that this is nothing but the post order traversal,
Yes.
right? So sometimes it is not exactly the pre-order or the in-order or the post-order traversal. What the pre-order traversal says is that first you process the tree, then you call the left subtree and right subtree, right?
Yes. You process
First
the
you
current
process the
node, then
root,
the left.
yeah. So sometimes what happens is that we process the root, then we call for the left subtree, then we reprocess the root, then we call the right subtree, then we reprocess the root again, right?
Right.
So it is neither pre-order nor in order nor post-order in that sense. So that's why I have kept it as recursion, right? But it is DFS in all the cases. All right. Can I say that irrespective of whether it is pre-order, in order, or post-order traversal, the memory model looks the same,
It is recursion, it is same.
right?
Well, I mean, if you're touching every node, then yeah, it's the same.
See, no, the memory model. So in case of pre-order traversal, first we will call the function for 5, root equal to 5. The call stack will look the same. That's what I'm saying, right? So first we will
Yeah.
call the function for 5, then it will print 5 and call the function for 3, then it will print 3 and call the function for 1. Let's ignore the nulls, then it will return and call the function for 4.
Right.
Then even 4 returns, 3 returns, and the function is called for 15, right?
Yeah.
Let's
So it's
let's
gonna be the same.
yeah, let's look at the call stack of in-order traversal. In the in-order traversal, first you call the function for 5, it will print nothing and call the function for 3. Then it will print nothing and call the function for 1. Then 1 will call for left, and then 1 will print itself, and then 1 will return. Then the function will be called, then 3 will print itself and call the function for 4. Sorry, it will not return, it will just print itself, right?
Yeah.
And then 4 will return, and then 3 will also return. Then 5 will print itself and call the function for 15, right?
Yes.
I mean, the memory model will look exactly the same. The only difference is that at every
The
call
order in
stack,
which
at
they're at.
every right, so at every stack frame, we are coming 3 times. First, when the stack frame is created, then when we are done processing the left subtree, we again come to this stack frame. And third time, just before deleting it, we also the execution comes to that stack frame. So if you are printing the value of root.data the first time when the control comes in the stack frame, then it is the pre-order traversal. If you are printing it the second time, then it is the in-order traversal. And if you are printing the third time, then it is the post-order traversal. All right. So from memory footprint, we cannot figure out whether it is pre-order, in-order, or post-order, right? We cannot figure it out from the call stack. Let's say you are given this tree, and what we want is in every node, we want to add the sum of all the nodes in the tree contained inside it. So for example, this 3 should be 3 plus 1 plus 4. This 6 should be 6 plus 9. 5
Okay,
should
so
be
for
5.
modification, you have to rebuild the tree from the bottom, so it's best to do in post-order traversal.
This 15 should be 15 plus 6 plus 9 plus 20.
I
All
know
right.
how to do this.
Why can't you do in the recursion same way, right? Like it's
Yeah, well, recursion post-order traversal, because you want to go down to the very bottom. Since 9 null, it'll be 9. Then you go, because you have to first modify the bottom of the tree first before you can go and
no, it's
modify
not
the
asking
top.
for modification, it's just asking for the total of that, right?
Yeah, so the best way to do that is post-order.
Yeah. Go ahead. How can we do it?
Okay. So
This should be a void function, right?
yeah.
Let's say the name of the function is update the tree, node pointer root.
Wait, but wouldn't you have to return root? Because you'd be changing it. Oh, but you can modify data.
Yeah, we are only changing the data of the root. We are not changing the node itself.
First, you you go down the left subtree, so you do update r.left. Wait, no. If the node is null, first you do the null check. Sorry.
Okay.
So if r is null, then do nothing, return.
Okay.
Okay. Otherwise, update r dot left.
Now the entire left subtree is updated, right?
Yeah. And update r dot right.
Now the entire right subtree is updated. Okay.
Yes.
The only node that is remaining to be updated is the root node.
Yeah. So then now you can Okay, wait.
No,
I know.
root is equal to
Root is equal to left plus right.
yeah, left plus right.
Okay.
But
So
then you
root
need to
dot
check-
data
It's not.
plus
Yeah, no, but
equal
you-
to
but
root
you
dot
have to check-
left dot data plus root dot right dot data. Is this what you're saying?
Yeah,
Yeah, but
but
you
you
have
have
to
to
check
check.
if each null, if left is null and
Yeah,
right is null, then add
great,
0.
great. So normally this is the mistake that people make, right? So we have to check that if root dot left is not equal to null, only then add root dot left dot data, and a similar check will be for the right subtree.
Yeah.
Man, this is very you simplified good. Now I understand a little bit binary tree. Earlier I was not. I didn't know all of this. This is good.
All right, great.
This
So
is good.
binary tree is the best data structure to practice recursion, right?
Yes.
Because it is natural recursion. So the more otherwise, binary tree questions are logically very easy if you are able to basically think recursively. So today we have just done the introduction of binary trees, and tomorrow, we'll practice more question on recursion. And if we get time tomorrow, then tomorrow we'll discuss level order traversal. Otherwise, maybe we'll discuss it day after tomorrow, right? We spend a lot of time on binary tree because binary tree is natural recursion, and recursion will be used in dynamic programming a lot, right? So
Okay.
you need to have a very strong hold on recursion to solve very complex dynamic programming or backtracking questions. Rakesh, you have any questions?
No, no, no.
All right.
This is first time I understand the binary tree, so it's good for me.
Thank you. All right.
Thanks.
Thank you. Stay then.
Thank you. Thanks.